Hello everyone. Welcome to the second lecture on distributions and descriptive statistics. Today we're going to talk about some common distributions and their distribution functions and how to plot them and work with them in MATLAB. We're going to talk about the central limit theorem, and then we're going to end on descriptive statistics. Today I'm going to talk about 6 random variables and their probability distributions. I'll talk about 3 discrete random variables and 3 continuous random variables. For discrete random variables, I'm going to talk about the Bernoulli binomial and Poisson distributions, and for continuous random variables, I'm going to talk about exponential, uniform, and normal distributions. To begin, I'm going to talk about the relationship between the Bernoulli binomial and Poisson distributions and the relationship between the Poisson and exponential distribution. During the section on the central limit theorem, I will also talk about the relationship between the normal distribution and all other random variables. So to help make some of these probability distributions a little bit more familiar, I'm going to talk about the different types of processes that they're used to model. So we've actually already met Bernoulli random variables. They're used to model things like coin flips, where you have heads and tails come out. So these are essentially binary 0-1 types of random variables. We've also already met binomials in the sense that if we have 3 tails, or 2 tails and 1 heads, and we want to add up the number of heads, in this case we get 0, in this case we get 1, and the distribution of those numbers, in other words our omega from last time, that is determined by a binomial random variable, and they are in fact sums of Bernoulli random variables. An example of a Poisson random variable would be a spike rate. So if I have a whole bunch of spikes, this is not anywhere near random enough, but if I look at the distribution of rare events in time, and I want it to be more or less completely uncorrelated, then these are called Poisson events. And the rate at which they come in, so if I bin this up into time bins that have the same width of, let's call it little t, then the number of spikes that I get in any one of these bins is going to be determined by a Poisson distribution. Some other examples of processes that produce things like this, in addition to neuron spikes, are things like radioactive decay, where the number of decays per unit time is determined by a Poisson distribution. So the next one is the exponential distribution. And in this case, an example of this would be the waiting times between spikes. So if I have 2 spikes and I want to know how much time there is in here, and then I have another set of spikes, right? If these spikes come from a Poisson process, or if decay events come from radioactive nucleus, the amount of time between any of these two is going to be determined by an exponential distribution. So we've already met uniform distributions. One of the most important examples of things that follow a uniform distribution are p-values under the null. And for normal distribution, things that are normally distributed are things like height, weight, intelligence, things that have some variance in the population. And also, very importantly, the mean of a sample is always going to be normally distributed, and we'll talk about that as well during the central limit theorem section. So before we jump into talking about the relationship between random variables and looking at their distribution functions, I wanted to sort of go over the anatomy of a distribution function so that it was a little bit more familiar, because there's some terms I'm going to use that are going to be important in the rest of the lecture. So this part should look familiar, this little f of x, and this is the probability density function. And this is the equation that defines it. But there's something new here that we didn't have last time, and that's this beta. And this beta is a parameter of the distribution, which can define some of its properties, such as the mean or the variance. And so this can be read as little f under x of x given beta. And what this means is that for any given random variable, this beta is going to be a constant, which defines the properties that I mentioned. But it also means that you can have multiple random variables that have different values for beta. And we'll see what this means later when we look at this particular distribution function with different values of beta. So the next part I want to talk about is this. This is just the domain. In this case, it is 0 less than or equal to x is less than infinity. And this just says where this distribution function is defined, or over what values of x it is defined. And lastly, we have restrictions on the parameters, which are important for making sure that this probability density function is actually a good probability density function in the sense that it integrates to 1 and is not negative at any point. Okay, so now we're going to talk about, in a little bit more detail, the relationship between these 6 random variables that we're interested in, and I'm going to highlight them for you. This is a big table of common distributions from Cassel and Berger, which you can find on page 627. And there's a lot of information packed in here, but the ones that we're going to focus on here are our Bernoulli, right, our binomial, our Poisson, our exponential, uniform, and normal. So let's start from the Bernoulli. You'll remember I mentioned a couple slides ago that binomials are just sums of Bernoulli random variables. Here's this relationship. So if you have a number of different Bernoulli random variables and you add them all up, their probabilities are distributed based on a binomial distribution. Similarly, going the other direction, and this is actually practically useful when we get to using MATLAB today, because MATLAB doesn't have a Bernoulli random variable for the reason that if you use a binomial random variable with n equals to 1, it's exactly a Bernoulli random variable. Then we have the Poisson distribution, and in this case, the Poisson distribution is equivalent to the binomial distribution when lambda is equal to n times p as n goes to infinity. So essentially what that means is that if you have a whole bunch of things that you're adding up, a whole lot of n, then the distribution is going to be more or less Poisson. So the other things to note here are that both binomial and Poisson have direct relationships to the normal distribution. We're not going to talk about that directly today, but the normal distribution lives in the middle of all these other distributions for a very good reason. Those are really the main relationships that I wanted to highlight. On this diagram, you don't see the relationship between Poisson and exponential random variables in that their waiting times between Poisson events. But just keep that in mind, that all of these things are linked together. All right, so now that we have seen sort of the high-level relationship between all of these random variables, let's quickly go over all of them individually, just look at their probability mass functions, and go over the MATLAB functions that you'll need. So the probability mass function for Bernoulli, which we've already sort of met, is just the probability of a success times 0 or 1, right? 0 or 1. and then it's 1 minus the probability of success. So this is the probability of failure. Right? Success, failure, and times the other 0 or 1. So if this is 1, this is 0, and if this is 0, this is 1. That's how that works. And this is what comes out. So let me now unpack all of the binomial functions, and this notation will be the same on all the other slides, so I'm not going to go through it. So these slides are going to be a little bit more for your reference. In case you wanted to look at Python or R, these are the equivalent functions. All right, so this means the command here, bino CDF, is the binomial cumulative distribution function. Bino inv is the inverse CDF. I'm going to go over that in a little bit after these slides, just to show you how that works, because it's useful for certain things like calculating p-values and confidence intervals. Bino PDF. In this case, this is a PMF, but MATLAB standardizes everything to PDF so that it's easier to write scripts. So this is pretty self-explanatory. And then Bino R&D, which generates samples from, in this case, a Bernoulli random variable. But remember, you have to use n equals to 1 for Bernoulli. And we can see that if we come back here, right? Remember, you add up a bunch of Bernoullis, you get binomial. Binomial, if you set n equal to 1, and with p, then you get Bernoulli of p. So that's Bernoulli. All right, now for binomial, in this case, this is the sum, right, of independent Bernoulli trials. So again, probability of success, probability of getting that value of x, in this case, this number of successes. X is the number of successes, so it's the probability of getting the success on a single trial raised to the number of successes. And you subtract the number of failures from that. So it ends up being in choose x times number of, it's p times, sorry, it's p, the probability of success to the number of successes. And in this case, probability of failure to the number of failures. Again, x is limited by n because you can't have more successes than the number of times that you're trying to succeed. One thing to note here about this is that at p equals 0.5, you get symmetric distributions. At p equals 0.75, you get right skewed, and at p equals 0.25, you get left skewed. All right, and again, you can expand these for the problem set. All right, now we meet somebody new. This is Poisson. Its probability mass function is for the probability that x is equal to x depends on a parameter lambda. In this case, that's e to the minus lambda times lambda to the x over x factorial. So what does this mean? Very simply, this is how you express rare events. So if let's say that on average in a certain unit of time, I expect to see 5 successes. That means that I get 5. So if I have 5 successes, and I want to know, okay, if that's on average what I get for rare events. Well, for one, if I want to know how often am I going to get only one event in this time interval, if on average I get 5. And the way that this is expressed is that you say, okay, I have 1, right? So if I want to know for probability that x is equal to 1, then I get e to the minus 5 times 5 to the 1 over 1. And so I end up with 5e to the minus 5. And it goes all the way down. So having drawn that, I think it'll be a little bit easier if I show you an example. So this is a visualization of a Poisson process, essentially. And if we look, if this is our starting line, right, or maybe let's make this our starting line, and we look over here, then within this unit of time, right, if this is our unit of time t, if I take the average of all the spikes in here, I will get some parameter lambda. Right? So when I can count them up, right? I got 1, 2 here, I got 2 here, I got 4 here, right? 1, 2, 4, 3. That's 3, 4. These are going to have a Poisson distribution. If I average all of those together, I'm going to get a good estimate for lambda. And so you can do the same thing over long periods of time as well. So if you just know that you have this many spikes of this unit time, you can get a very accurate estimate for the average spike rate of a neuron. All right, so now let's talk about the exponential distribution. We actually met this fellow earlier in our anatomy of a distribution function. In this case, right, we have 1 over beta times e to the minus x over beta. Putting 1 over beta out front here normalizes this so that it integrates to 1. And if you have larger betas, you have a higher mean. Right? So let's go back to this example here, because this links both Poisson, right, and exponential. So for Poisson, right, Poisson gives you the average rate. Exponential, however, gives you the distribution of the times between Poisson events. So I actually cheated here. I generated this raster using an exponential random variable. So these times will be distributed by an exponential. All right, uniform. In this case, it's just 1 over b minus a. So width of 1, it's going to be 1. If this is a width of 3, this is a width of a third. This has a width of a sixth. This is going to be 1.666 repeating. Again, uniforms show up, especially for the distribution of p-values under the null hypothesis, which is why people worry when you get a little bump over here at p is less than 0.05, and the fact that they're not uniformly distributed when people are accepting null hypotheses, i.e. publishing papers. And last but not least, we have the normal distribution. In this case, it is given with 2 parameters, mu and sigma squared, representing mean and variance. It's 1 over the square root of 2 pi sigma, which normalizes this value here to 1 when you integrate. And then you have, in the exponent here of e, you have 1 minus x minus mu squared over 2 sigma squared. Okay, so what is this? Really, I think the main thing to take home from this is that this x minus mu tells you the centering of the distribution. So for the black one, right, this is a standard normal, it's 0, 1. It tells you where it's centered, and it makes it symmetric. So that is what this this term up here, the x minus mu squared, is what makes this symmetric. So again, right, mu minus 2, symmetric about that. And it's this part here. And the width is determined by the sigma squared here. So we're going to talk about this in the next section, but essentially any repeated measure with finite error is going to have a normal distribution. This is especially useful for means, and we'll talk about that extensively in the central limit theorem portion. Some naturally occurring phenomenon that appear to have a normal distribution are height and weight. So I think it's very interesting that biological processes seem to produce numbers that appear to be normally distributed. All right, so this is it for distributions. Next, we're going to talk about the central limit theorem. Okay, so now that we've seen some of the distributions of random variables, let's talk about the central limit theorem. And to motivate this, I'm going to show you a series of distributions, of empirical distributions, and then we'll come back and talk about what we've just seen. All right, so let's look at that again. Let's focus on this number up here. I'll circle it even. So what has happened here? Let's just play this quickly. It looks like as I increase the number of averaged measures, I haven't said of what yet, this thing, which looks suspiciously like an exponential distribution here, converges to a standard normal distribution. So what's going on? All right, so let me tell you now how I produced this. I took, in this case, I took the sum from I equals 1 to 1 of xi, and 1 over n. Right? So in this case, n is 1. Where xi is distributed as exponential of 10. And to make it line up with the standard normal, I subtracted its mean and divided by its variance. So I did this to get this empirical distribution here. So as you can see, right, this is an exponential which is shifted over. This distance here is 1, sort of as we would expect. And the variance, again, is also 1. So then what happened for this next picture? Right, so now I'm adding together two random variables. So this time, I have x1 plus x2, where xi is distributed again as exponential of 10, and I'm dividing by 2, and then I'm sampling from these to generate this distribution again. Right? For 3. Again, 3 here, add x3. 10, okay, this time, we're summing from I equals 1 to 10 of xi, this is 1 over 10. And then we got 10,000, or 100, right, 1 over 100, sum from I equals 1 to 100 of xi. And finally 10,000. So now that we've seen this, this is what I'm doing, and then the way that I get all of these numbers here is that I do this, right, 30,000 times. So I repeat this process 30,000 times to fill in all of this data here so that we can see, in the limit what happens. So it basically says in the limit, right, where I'm creating an empirical distribution when I only have x1 over 1, this is what I get. When I have x1 plus x2 over 2, this is what I get. Right? All the way up to 10,000, where I get something that looks suspiciously like the standard normal. So what is actually going on? And there's a theorem, the central limit theorem, is what explains this. And the simplified statement of it is that the sample mean of a sequence of independent and identically distributed random variables is normally distributed. So said another way, the mean of any sufficiently large sample is normally distributed. So here's here's what I was writing on the previous slide, where I have defined x bar of n is equal to 1 over n times the sum from I equals 1 to n of xi. Right? So in this case, n would be 10,000. And so there's just two other things that we need. Right? We need to know the expected value of the xi's, and we're just going to define this as mu. And we want to know the variance of the xi's, which is sigma squared. And it just needs to be greater than 0. And so let's then unpack this statement here. So square root of n times x bar n, otherwise known as our sample mean, with n samples from any random variable, subtracted by the component random variables mean divided by the component random variables standard deviation, has limiting standard normal distribution. Right? There's in part of this definition, you take the limit as n goes to infinity, but what really matters here is that having this form around this x bar n means that by definition, x bar n has to be normally distributed. So there's, in this case, the standard normal distribution is this normal of 0, 1, which you can see here, right? But when you take a normal, any normal random variable, and you do this transformation on it, and you get normal 0, 1, or you, this implies, right, that x bar n is distributed as a normal mu sigma squared, which is really useful for us in science because we work with means all the time. So if we want to compare the means of two different processes, then we know that we're safe, right? Because the mean will be normally distributed. And the thing is that you don't even have to know mu and sigma squared for the original generating process. All you have to know is that your n is large enough, right? Which leads to this question: what counts as a sufficiently large sample? And I can't answer that question. The rule of thumb, people will say, oh, it's around 30 or it's 100, and you can look here and you can see, okay, we're at 100. The space that we're missing here is tiny. Similarly, over here, we're not missing much. If we're at 10, on the other hand, it's pretty clear that there's some significant territory missing here, and even more here, and you can probably compute a non-zero skewness for this empirical distribution. But in general, the central limit theorem is going to be very important. It's very important for the all of the tests that Vlad and Vee are going to talk about next week, and it guarantees that if you can show that your data is normally distributed, then there's a whole bunch of really nice tools and tests that you can use, and it basically says, if you can average together, 10, somewhere between, we'll say, somewhere in between 10 and 100 different measurements of the same quantity, right? This xi has to be from the same generating distribution. They can't be from different distributions. So I can't have an exponential be one, or an exponential of 1, and then another one be exponential of 10, right? I can't. This doesn't work. They all have to be the same, right? You can't do that. But as long as the underlying process is thought to be the same, then we can add them up, and our means are good, and all of the tests that are based on assumptions of normality are met, and you don't have to worry about it. And you can worry about it, but the formal way to think about how much you should worry is how far off you're going to be. So here, right, if you're interested in whether there are outliers that you're missing out here, 10 may not be enough to have determined the outliers. Whereas if you're at 100, you have enough coverage, and the error there is going to get smaller with the increased number of measures, or the increased number of random variables that you are averaging together. So now we arrive at last at descriptive statistics. So this table very quickly is just the name of the statistic, its mathematical definition. This is mostly here for your reference. I'm going to show you some pictures of them, and then the MATLAB command, which is going to be the most useful. So the ones that we have already met are mean, variance, standard deviation, max, min, kurtosis, and skewness. One new one since last lecture is interquartile range, and it is basically just, if you look at where it's the distance between where 25% of the probability in your distribution is and where 75% is. And I'll have a picture of that for you in just a minute. Okay, so just as a reminder, I'm going to draw the mean, variance, the standard deviation, the max, and the min for some example distributions. All right, so using our central limit theorem example here, we can see that if we look, this is going to be the min. The min is whatever value is the minimum in an empirical. And for most continuous distributions, there is no max and there is no min. There may be a min if it's a one-sided distribution like the original exponential. The mean of the sample is going to be right here. It's where the center of its weight is. The standard deviation for this, right, is going to be 1. It's going to reach out here. But a reminder that the variance, right, the variance is squared. So in this case, it's going to be because note that this is not actually symmetrical. I have to draw the variance not as a square here, but it needs to go all the way up to 1 here from 0 to 1. So this is the variance. It's an area. So now let's look at interquartile range, kurtosis, and skewness. And the visual representations for these are here. And so this is interquartile range, IQR up here. And the way it is defined, right, is that it is where the cumulative distribution function, here this diagram shows the the probability density function, but in the cumulative distribution function, where 25% of the probability lies over here, and 75% of the probability lies here. So let me draw this. So we have, right, 25% of the probability lies to the left, and that's quartile 1, and 75% lies here. So it essentially is the distance between these two, where 50%, right, 50% of the probability lies, the central 50%. So that's what interquartile range gives you. Now, kurtosis is about the tailedness, if you remember from last lecture. And in this example, the variance of this distribution is kept constant while the kurtosis is changed. And as you can see, the tails on the blue line are much, much shorter than on the green or the black lines. So that's sort of what we mean by it, the tailedness of a distribution. And lastly, we have skewness, which has to do with sort of the centrality of the distribution, or the symmetry of the distribution. So in this case, over here, we see something that is negatively skewed, i.e. it has more probability at lower values, and positive skew has more probability at higher values. So those are the measures that we're going to use. And now we're going to jump into MATLAB and check out some of the stuff that we're going to do so that you've seen it before you do it on the problem set. All right, so once you have MATLAB up and running, let's just go through the basics of what we're going to do here. And you can watch this a couple of times. You can look up some documentation on it, but I just want you guys to have seen this at least once. So assignment in MATLAB works like this. And I say x, and I want x to equal something. So I do x equal 1, I get this. If I want to print what comes out, I leave the semicolon off. For what we want today, because we want to be able to plot distribution functions, we are going to want to have x equals, let's say, -5 is the start. Then we have the step size. Let's say we want a step size of 0.01, and we want the stop to be 5. And we get a bunch of numbers that come out. So this is x. X is now an array that starts at -5 and goes to +5 in increments of 0.01. So I can suppress that by doing this. So then we want to use this to plot a function. So if we want to plot a function, we just use plot. So if I just plot x, it appears over here. Now I'm going to do this with an extra command so you can actually see it. You probably won't need it. Right, so there we go. Now the other thing that we can do is plot a function, right? So the signature for plot would be xy, like this. Now I'm going to get an error when I do this, but let's say I set y equal to norm PDF of x, right? These numbers are the values that come out for norm PDF of x. If I want to suppress it, I do that. Then I can do plot of xy. And lo and behold, I get something that looks like a normal probability density function. So that's how to use the plot, and that's how to get an array of numbers to start with. Let's look at the other thing that we want to do, which is plot histograms of samples from random variables. So in order to sample from a random variable, let's use the normal again. We would have, let's do samp equals norm R&D. You can hit tab to autocomplete, and it will show you all of the possible completions. So in this case, I want norm R&D, and then the value that I want, or what I'm going to put in first is just the size, right? So let's say I want 100 of these, or let's do 10 so it doesn't overflow the screen. Oh, I don't know what I'm doing. This is the point at which you usually look up the documentation. And see what happens. It works like this. MATLAB norm R&D. Normal random numbers. And it turns out that what we want is we have to give it a mu and a sigma, and then we have to give it the number of dimensions that we want. So this means let's do normal 0, 1, and let's say we want 10. All right, here are our numbers. So now if we want to plot a histogram of this, we do hist of sample. And here's our histogram. So we can also do this with another histogram where we have 1, and then we have that. Actually, if you put in a 10 by itself, I think it gives you a 10 by 10 matrix. So in this case, I want one row with 10 columns. I get my sample, and then I do hist of sample, and here that looks more like a histogram that we're used to seeing. So let's do this now with even more samples. And here we have a histogram for a normal distribution. There, you can look up the extra documentation for how to use histogram to change the number of bins and things like that, but we'll go over that in class as well. So right, we can also do this for other exponential random variables. So if we wanted to do exp equals exp R&D, right? Then in this case, I only give it one parameter, lambda or beta, from our previous example. And let's do 10, and I want one row and 10,000 columns. And then I can do, so I'm going to show you this because this is useful for plotting things on top of each other, which is going to be important for part of the problem set as well, which is I want to plot something over that. So I type hold on, and then I can type plot, or then I can type hist exp samp, hit enter, and it fills in there. Now, we're not going to be able to see it because the exponential distribution does not overlaps poorly with the normal 0-1 distribution. So I can then type hold off, and if I type hist exp sample again, I can see that this is the distribution that I get out. So that's most of what you're going to need to know for this. We're going to put some of it together for the problem set, but hopefully this will get you started so that you've seen how MATLAB works and what you can use.